Okay, so today we are going to do a review of functions. So first we have a little vocabulary we need to talk about. It says here that a function is a correspondence which assigns each member of the domain to exactly one member of the range. In other words, no x values can be repeated. So a few key things we need to highlight here is that it says that the domain is matched to exactly one member of the range. In other words, the x values cannot repeat. So if you have any x values that are listed more than twice when listing your domain, then that means you do not have a function. Okay, it also says here, in any function there exists a cause and effect relationship. Your cause is your independent variable, which is always going to be your x value, while the effect is always your dependent variable, which is the y. So they give the example y equals 2x plus 3 and say the value of y depends on x. That's because depending on what value I happen to plug in here or substitute in here for x, my value of y in turn is going to change. For example, if I were to put a 1 in here, then I would get an output of 5. But if I were to change this value out for, let's say, a 2, then I'm going to get an output of 7, right? So this value is directly dependent on the x. Some other terms that are often associated with our functions are, first, relation. A relation is any set of ordered pairs. And remember, ordered pairs are just coordinate points. So you've got some points making up a relation. Your domain is all of your input values, or in other words, all of your x. So if I ask you for the domain, I'm asking about the x values, while your range is the set of output values, which is your y's. So if I ask you for range, I'm asking about your y values. They also remind us here that zeros or roots, also called x-intercepts or solutions, are a value of the domain, which again is our x's, that make the function y equal to 0. Okay, well, y equals 0, if I were to see that on a coordinate plane, would be the x-axis, right? The x-axis is y equals 0. So if you have any point on that line, for example, if you had a point right here like this would be an x-intercept or a 0 or a root. Now it says that these are what we consider real roots, because if you recall in Algebra 2, you talked about imaginary numbers as well, okay? So you can also have what are called imaginary roots. So these would not be on our x-axis, but if they are on the x-axis, we know these are considered to be zeros or roots. We also have what's called function notation, which is f of your independent equals your dependent. So typically our independent is x and our dependent is y. So you most often are going to see this is written as f of x is equal to some function. Basically, f of x and y equaling some function can be used interchangeably, but this one is what we call function notation. All right, and then we have our restrictions on the domain. So this is what we're going to be focusing on today. There are a few things that can restrict our domain, which, remember, are our x values. Okay, the first has to do with the denominator of your fraction. It says here your denominator cannot equal 0. So we actually had a question like this on 1.2, day 2, where they said that you ended up with, I believe it was 7 over 0 whenever you found the slope. And we know that we can't have 0 in the bottom of a fraction, so we said our slope was undefined. So anytime you have 0 in the bottom of a fraction, it is undefined. Okay, so that would be a restriction on your domain if that happens. Then it also says for point B, that the square root of some value is going to have to be greater than or equal to 0. All right, so if that's the case, what we're saying here is that any number you're taking the square root of has to be a positive number. The reason being, whenever you take the square root of something, you're asking yourself what multiplies times itself to give me that value. Well, if I was taking the square root of 16, okay, that would be 4, because 4 times 4 is 16, or negative 4, because negative 4 times negative 4 is also 16. However, if it was a negative 16, there is nothing that multiplies times itself to give me a negative. So, if we're taking the square root of something, we need it to be a positive number. Otherwise, it's what we call imaginary. And then our last restriction has to do with real-world situations. So, based on whatever the scenario is that they give to you, one or more of your answers may not make sense. For example, if you are supposed to be solving for the length of something and you come up with 2 solutions and one of them is negative, we would know that length typically is not negative. So we would go with the positive solution. But today we are mostly going to be looking at these 2 restrictions and solving algebraically to determine what the domain of a function is. So on number 1, we've got 1 over x squared minus 1. Okay, so when we've got 1 over x squared minus 1, this would be a fraction, which would mean we're looking at a possibility of a happening. A being that it says the denominator cannot equal 0. So that's what we need to keep in mind. If I'm listing all of the domain, so I'm listing all the possible x values, I need to be sure that I remember my domain can't be anything that would give me 0 in the denominator here. All right, so I've got x squared minus 1. That is a difference of squares, so I could factor it if I'm wanting to simplify. And then I would ask myself, what could I plug in for x to get 0 in this parenthesis? Well, a positive 1 and a negative 1 would give me 0. And if this parenthesis becomes 0, 0 times anything in the other would give me 0 in the denominator. So negative 1 would be an issue. If I'm looking at this parenthesis at this x, I wouldn't want to put a 1 there, because if I put in a 1, 1 minus 1 would make this entire parenthesis 0, and 0 times the other factor would turn the entire denominator into 0. But there's nothing else I could put in either of those places that would make that happen. So that means every other number, any number you can think of, would be a part of the domain. It would take us a really long time to list all the numbers that would work. So what's going to be easier for us to do is say everything works except x cannot be equal to positive and negative 1. So this would be our domain. All right, for number 2, we've got the square root of x squared minus 4, which is going to be causing us to look at that restriction from part B, saying that any square root we take has to be positive, got to be greater than 0. So whatever square root I take here, in this case, x squared minus 4, needs to be greater than or equal to 0. All right, so if I was going to solve this, I could factor because it's a difference of squares, or I could solve it like I would any equation by getting x by itself. So I'd have x squared is greater than positive 4. I'd move it over by adding, and then I'd need to take the square root. And the square root of 4 is plus or minus 2. All right, so let's see what happens if I were to plug in plus or minus 2 into our function. So we would have the square root of negative 2 squared minus 4. Well, negative 2 squared is 4. 4 minus 4 is 0. And 0 is greater than or equal to 0, so that works. Okay, if I plug in a positive 2, I would have the same outcome. 4 minus 4 is 0, which is greater than or equal to 0. So both of these solutions do work. But remember, we said we need to find out where it doesn't work so we can be sure and exclude that. All right, so We know 2 and negative 2 work. Let's pick a number that is between negative 2 and 2 and try that. So maybe we try negative 1. So negative 1 squared minus 4. Well, negative 1 squared would be 1. 1 minus 4 is negative 3, which is not greater than or equal to 0. So that did not work. I could try a positive 1 as well. I'm going to get the same outcome. So it looks like when you try out numbers that are between these two, that's when things don't work. Let's try something that is not in between them. So maybe negative 3. Okay, so negative 3 squared is 9. 9 minus 4 is 5, which is positive, so that would work. Same if I do larger than 2, all right? I would still get 5, still works. So basically, we're saying that 2 and negative 2 work. Anything larger or smaller than those two values work, but the things that are in between did not work. So we're saying that x is going to have to be less than negative 2, like our negative 3 was, or x is going to have to be greater than positive 3, like we showed here. But the things in between don't work. All right. So if we flip it over on the back, now that we've practiced solving some algebraically, we're going to take a look at two graphs and determine the domain and range based on the picture. All right, so for number 3, if I'm listing the domain, that's all of my x values. So my furthest x value would be this point right here. Okay, so at this point, I am at negative 8. Okay, but then it looks like there's nothing happening at negative 7, nothing at negative 6, nothing at negative 5. But when I get to negative 4, there is a point right here. And then that point continues to 0, stops at 0, but picks up right here and continues all the way to here. So it looks like we have something existing all the way from negative 4 over here, all the way to positive 4 over here. So x also exists from negative 4 to 4 and every single decimal point in between. So every number that exists between here. Now at negative 4, that was a solid point, so I need to include it. So I add that equal sign. But over here at positive 4, that point was open. All right, after 4, there's nothing at 5. At 6, we've got another point up here. So I'm going to add 6 to that list as well. All right, now we do the same thing for range, which is our y's. So looks like this entire little line going on here exists at 1. There's nothing happening between 1 and 2. I do have a point at 2, but nothing between. So I'm just listing them at this point. Got another thing going on here at 3, but nothing in between. Looks like we don't have anything at 4, but I do have a point up here at 5. And then another point up here at 6. But none of those were continuous lines, so we're just listing their values. All right, zeros. We said a 0 is where you intersect the x-axis, or the line y equals 0, which for us would be this line right here. And it does not appear that our function touches that line at all. So that would mean we do not have any zeros. Then the last question we ask is this a function? Remember, whether or not it's a function is based on if any x values repeat. So we have a close call right here on this line, but this point is open and this point is solid. So technically, those don't repeat because this open point is everything up until 0. So no repeats there. We do, however, have one right here because this is a solid point and this is on a line, so it is also a solid point. So we do have these two x values repeating right here on this line. Therefore, this is not a function. All right, number 4. On number 4, looking for that domain, which is our x's. And it looks like over here, this arrow shows it going infinitely to the left. This arrow shows it going infinitely to the right. And it looks like everywhere in between those arrows, there is something continuous, right? We've got this entire line here. We've got this point. So although this is open, it is continuous because of this. We got this line all the way to this open point, but then this picks up here and continues up and down to this arrow. So we are continuous in all places. There are no holes or open spaces, and it is continuous in both directions. Therefore, our domain is everything, so all real numbers. And it's going to be the same with our range. Those arrows point up and down, and there aren't any places on the y-axis between the arrows that don't exist. So it is also all real numbers. And then finally, we are taking a look at our zeros or our x-intercepts. So it looks like we've got one here, here. We said we had a point here, and we got another one over here. So I'm going to have to list all those out. So furthest from the left, we have -9, 0. Then we've got -3, 0. We've got another one at 0, 0. And then finally, we've got one at 12, 0. And then the last question we ask ourselves is this a function? So that's when we do the vertical line test. We're running our pencil across. It does not appear that there are any overlaps because like we discussed earlier, this is not an overlap because this point is an open circle while this one is filled in. So this one does pass that vertical line test and is a function.